Hello, everybody. That's a hot mic. Okay. Happy Halloween and welcome to Community Conversations. I'm very pleased to welcome our speaker today. Morgan Salisbury was born in Twin Falls, Idaho, and received a bachelor's in geology from the University of Idaho. He received a PhD in geology from Oregon State University and a master's of geology from Central Washington University. And he's been teaching earth science at LCC since 2016. So please welcome Morgan Salisbury.
Thank you, everybody. Thanks for coming. Happy Halloween. Um, Thank you for the introduction. As she mentioned, my name is Morgan Salisbury. I teach earth science and geography here. Maybe I can skip to the next slide. I've got some degrees. They're all in geology. After I got my PhD, I did a couple of years in Durham University in the United Kingdom, studying the volcanoes of Bolivia. I think I've been to Bolivia now 12 or 13 times, kind of lost track. I've spent more than a year on the ground there, maybe getting close to a year and a half now. I kind of stopped keeping track. But I will be going back. In the spring term, I'll be gone because I'm going to start a Fulbright scholarship collaborating with the university in La Paz, Bolivia. So how many of you know where Bolivia is? You just looked it up. All right. All right, let me talk a little bit more. I just wanted to mention that I am going to be doing both research and education during my time in Bolivia coming this spring. If you've taken any of my classes, you've probably colored some maps. I am going to take that same teaching philosophy to Bolivia and share some of the maps of the local Bolivian geology that I've been making. Collaborate with my peers. We're also going to go out in the field and collect some samples from some Bolivia volcanoes. Here's an example of a map some of you in this room may have colored. I'm really into maps. I'm also into field trips. I know we couldn't get our field trip off the ground this year, but normally we have field trips. I'm still going to try to figure out a way to make up that field trip. But next quarter, we'll be back on track for sure. So if you're interested in taking a geology or geography class and you like taking field trips and coloring maps, consider one of my classes. Okay, this talk I'm going to be focusing first on the geography of Bolivia, and then after that we're going to get a little bit more detail into the geology of Bolivia. Geography tends to focus more on the landscape, where things are, why they are, and geology is a little bit more looking at the rocks themselves and Earth's history. And the way you remember that, geology rocks, but geography is where it's at. Okay. If you're not familiar with Bolivia, it is here in the center of, let me put the microphone. Excuse me. All right, that should help. The Bolivian Altiplano, I'll get into more of the geographic details. It's kind of the Central Andean Plateau and the Bolivian Altiplano, or sorry, just the Altiplano, can be used interchangeably as geographers make a distinction between the two. I'll get into the details here, starting just a little bit about the geography of Bolivia. It's located in the center of South America. It's a landlocked country. It's pretty big. It's 424,000 square miles, which is the size of Washington, Oregon, California, and Idaho combined. But it has far fewer people, as a total population of 12 million, which is about the same population as Oregon and Washington combined. Bolivia is located entirely within the tropics, so it gets lots of sunshine year-round. It also has quite a bit of the Andes in it. The western part of the country is dominated by the Andes, and the eastern part is dominated by the lowlands. In the northern part of Bolivia, we've got Amazon rainforest, and in the southern part, we've got more of the Chaco dry forest. Okay, here's a cool digital elevation map. It's exaggerated, of course, but it really shows the topography of South America. And I overlaid the border of Bolivia here. You can see it really is divided between the Western Highlands and the Eastern Lowlands. The Eastern Lowlands make up about 70% of the country, whereas the highlands make up about 30% of the country. And there's extreme elevation difference here. The Eastern Lowlands are around 1,000 feet on average, whereas the Western Highlands range from about 12,000 to 21,000 feet elevation. All right, zooming in just a little bit here. We've got the Andes Mountains, the Central Andean Plateau. About 50% of Bolivia is tropical rainforest and savanna, mostly tropical rainforest up here. You get down to the southeast, it turns into more dry forest. And then about 30% of the country is the Bolivia highlands. Some of the major cities, the capital, or the administrative capital anyway, La Paz, has the majority of the population, about 2.2 million. The other big city is Santa Cruz, which is down in the rainforest, which has about 1.9 million. Other major cities are Cochabamba, Oruro, and Sucre. And there's a pretty big economic and cultural divide between the highlands and the lowlands, as you might imagine. The highlands, a lot of potatoes, quinoa, and hard rock mining form big parts of the industry, whereas in the lowlands, it's more sugarcane, cotton, soybean, and then oil and gas exploration. So quite a bit of two different economies, essentially. This highland-lowland divide is also seen in the geography. These are summer temperatures. So we're in the southern hemisphere. The eastern lowlands are quite a bit hotter than the high elevation. They receive a lot more rainfall. And then I just put in the last presidential election map by party, showing a political divide between the lowlands and the highlands as well. All right, I'm gonna break down the geography a little bit more, divide up the eastern lowlands here. And as you move to higher elevation, you get to the Yungas, which is kind of a transition between the lowlands and the highlands. The highlands begins in the east with the Eastern Cordillera. And in the middle, we have the Altiplano Basin. And on the western edge of Bolivia, at least, we have the Western Cordillera. And from there, it goes down to the Pacific Ocean, mostly in Chile and Peru. I'm going to kind of go through these a little bit one by one. The eastern lowlands dominated by the Amazon rainforest. This river, I'm not sure the name of it, but I was flying from Santa Cruz to Miami. This was out the window. Pretty typical. You can't really see this, should be green and very rainforesty. The major city of the lowlands, Santa Cruz. 1.9 million people, as I mentioned. Notice it's nice and flat and quite green. Remember that as we move upwards. Moving at higher elevation to the Yungas. I put a picture of Machu Picchu, which is in neighboring Peru, but it's probably a place in the Yungas region that you've probably heard of before. This is dominated by a really rugged topography and cloud forests. So we still get a lot of rain. We get actually some orographic rain as the clouds are moving up towards the mountains. The winds at this latitude are moving from east to west. And just a kind of a cross-section view of the rain shadow effect that's going on here with the plateau. This would be the Central Andean Plateau. Winds are blowing from east to west. As the moisture-rich air reaches the mountains, it goes up, it cools down. The air can't hold that water moisture anymore, and it rains. So we got the Amazon rainforest and Las Yungas on the eastern side. But by the time we get to the highlands, it's pretty much too high and too cold for much precipitation. And we got a rain shadow desert here in Chile on the western edge of South America. This is an image looking from an airplane eastward towards Bolivia. Here's Chile and the Atacama rain shadow desert. And the Bolivian border would be right around those volcanoes with the Western Cordillera. And this topographic change here is the largest topographic change on Earth over a distance of less than 200 miles. So from sea level, I think to those mountains, it's just over 100 miles. To the highest peaks are about 26,000 feet. All right, here's a Google Earth image looking from the east to the west. You can see the Amazon rainforest down here with the meandering rivers. And as you move upward, you get to Las Yungas and a city I'm going to highlight in a moment, Coroico. And the forest line here, because we're in the tropics, it's pretty high elevation. It's 11,000 feet. For reference, what's the timberline here in Washington? Any guesses? Any? Oh, I think it's much less than 12,000 feet. I think it's like 5,000 feet, 5 or 6, kind of depending where you are, north or south. Yes.
They talk on the news about where the mountain passes are, and they're at about 4,000 feet.
Yeah, and timberline would be a little bit higher than that. I think we're at, anyway, we're not higher than 6,000 feet timberline. That's because this timberline is really high because we're in the tropics. And then once you get above that timberline or the forest line, you can see that you get to a much drier climate where you get to the Eastern Cordillera, the Altiplano, and then the far west in this image would be the Western Cordillera. So my next image is going to show some of this Coroico, or the city of Coroico. It's a beautiful city in the mountain kind of cloud forest region. We're about 5,000 feet elevation here. And Coroico is famous for its death road. Used to be classified as one of the most dangerous roads in the world, if not the most dangerous road in the world, with I think they were getting around 200 fatalities per year until they finally built a more modern highway. And now this highway, you can still go on it. It's mostly for tourists now and bicycle riding. If you're into a bicycle adventure, try out the Death Road. Not as many people die on it anymore, but they still do. All right, so that's the Yungas region. We're going to move higher elevation to the Eastern Cordillera. This is another Google Earth image. The highest range of the Eastern Cordillera is the Cordillera Real, which is not far from the capital city of La Paz. And this is what the Eastern Cordillera looks like from the Altiplano. So we're looking to the east here. The Altiplano elevation is about, here is about 13,500 feet, and the peaks get up to about 20,000 feet. Bolivia has a significant number of tropical glaciers, which I'm going to mention in a couple slides. It's one thing that I think we kind of forget about. There are a lot of glaciers in the tropics. So I don't know about a lot. There are a significant amount of glaciers in the tropics, but you have to go at really high elevations to get there. Here's Murata. You can see the sedimentary layers here. All right, so here's the capital city of La Paz, built kind of right at the border between the Eastern Cordillera and the Altiplano. And the highest point in the Eastern Cordillera is this mountain, which is quite famous for the capital city of La Paz, Illimani. Everybody from La Paz is very familiar with this mountain. It's on all kinds of beer promotions, cement promotions. Everyone's got a tattoo of Illimani. It's by far the most famous mountain in all of Bolivia. And there's Illimani. You can see it completely just dominates the skyline on a clear day from La Paz. La Paz is a beautiful city if you ever get a chance to visit. It's a quite vertical city, and to alleviate some of the traffic and transportation problems, in the last actually 15, 20 years now, they've developed this teleférico system, which can zip you around pretty much anywhere in the city in a matter of minutes. The fare is only about 50 cents, so it's quite affordable, and it's quite beautiful. You can see here, this takes you downtown. You can travel from the highlands to the higher regions to the lower regions in a short matter of time. You can imagine the roads in this city are not very direct, and it's much more time efficient to take these teleféricos. This is me a while ago. Okay, moving on to the Altiplano Basin here. Oh, wait, No, I'm not. I want to talk more about the tropical glaciers of the Eastern Cordillera. The Central Andes is home to about 90% of all tropical glaciers on Earth. 22% of those are in Bolivia, with the majority are in Peru. This is a major issue for the inhabitants of Bolivia. It provides, in total, the tropical glaciers in the Andes provide fresh water for 80 million people. And most of the inhabitants of Bolivia, and about 50% electricity of Bolivia and Peru. The problem is that the tropical glaciers are retreating, they're disappearing. Some of them are already gone. Most famously, this ski resort, which is at the outskirts of La Paz, Chacaltaya, is no longer a ski resort because it no longer has snow and ice to ski on. Bolivia has lost 40% of its glaciers in the last 40 years. And at this rate, only has about 50 more years, give or take, until it runs out of glaciers altogether. And you can see that, you can imagine that's going to be a huge problem. The Chocayapu River, I'm pronouncing that right, also known as the La Paz River. This is the water that is the primary freshwater source for the entire city of La Paz, which has 2 million residents. And you can see it's not a very big river. You could almost jump over it in places. So as the glaciers retreat and they lose this fresh water, it's already becoming a problem, but it's going to become a much more significant problem as they lose that freshwater source. All right, now moving on to the Bolivian Altiplano. The Altiplano Basin extends up into Peru. This is an internally drained basin, meaning that all rain that falls in this region will not make it either to the east, to the Atlantic, or to the west of the Pacific Ocean. If it's in the northern part, it'll end up in Lake Titicaca. And if it's in the eastern part, it'll end up in these smaller lakes and salt flats. In the north, we have Lake Titicaca, which is the largest high elevation lake in the world. And in the south, we have the Salar de Uyuni, which is the largest salt flat in the world. Here's a picture of Lago Titicaca from the town of Copacabana. That's a pretty significant tourist town. And it's also home to the Bolivian Navy, because they're landlocked. They don't have any access to the ocean. They need to base their operations out of this lake here. Just for reference, Lago Titicaca is the 18th largest in the world by surface area. And of these, it is by far the highest in elevation, with a lake level of 12,500 feet. Okay, the salt flats in the southern part of the Altiplano, largest salt flat in the world, as I mentioned, the Salar de Uyuni, it's about 12,000 feet elevation. And then the Salar de Coipasa, I think it's in the top 5 or top 10 of the largest salt flats in the world. And here's a picture of this salt flat. It's a very popular tourist destination. If you ever get the chance to visit Bolivia, make sure the Salar de Uyuni is on your itinerary. This is what the parts of the Salar can look like during the summer rainy season. It can flood, gets a few inches of water, and then when it dries up, it leaves behind, whoops. Get me out of that. You get me out of that somehow. Yes, please. Okay. And then when it dries up, it leaves behind its dissolved salt content, leaving this nice salt flat. Okay. Moving first to the Western Cordillera. And the Western Cordillera is famous for its volcanoes. It's quite different than Eastern Cordillera, which is made up of folded bedrock, mostly sedimentary rock. The Western Cordillera is almost entirely volcanic rock and volcanoes. These red triangles show volcanoes that have had activity in the last 10,000 years. And then if you go back a little bit further in time, the last 2.6 million years. These yellow triangles show the active volcanoes. So this is a little bit about what the Western Cordillera looks like. This is from the Altiplano, and then you've got this volcanic range to the west. And let's see here, for reference here, the Altiplano at this location is about 14,000 feet elevation, and then the volcanoes add about another 6,000 feet to that. The tallest point in Bolivia and the tallest point of the Western Cordillera in the Bolivia region here is Sajama volcano at 21,000 feet, which rises about 7,500 feet above the Altiplano Basin. Recently, last December, we took a trip to Bolivia with my wife and my child, and I was very excited to show my daughter Sajama volcano from the airplane because that is her name. We named her Sajama after this volcano. So she was only 2, and I was like, Sajama, look, it's your volcano. And she was kind of into it, but I think I was a little bit more excited to show her the volcano than she was. But this was the first time we got to bring her down to Bolivia since she's been born. So it was a really fun trip. Okay, moving further south on the Western Cordillera, we get to this region here, which is where the Altiplano meets the high elevation region of Argentina and Chile, which is known as the Puna. So collectively, this is known as the Altiplano Puna Volcanic Complex because it's pure volcanoes here. And I'll zoom in just a little bit to show you some of these volcanoes, just to get a sense of the scale. So each of these volcanoes here would be about the size of, say, like Mount Rainier, more or less. You can see there's some salt flats here in between them. It's just very, very, very volcanically active. And I went down here to study the volcanoes for my PhD between 2006 and 2008. And specifically, we are looking at the supervolcanoes. So you're all familiar with Yellowstone being a supervolcano. There are about 6 supervolcanoes here in this image. And just for some reference, a supervolcano is defined as something around about 500 to 1,000 times larger than the May 18th eruption of Mount St. Helens in 1980. So these are very big explosive events. So these are explosive eruptions, by the way. For reference, this would be kind of be a normal volcano, like Mount St. Helens or Mount Rainier, with a normal sized magma chamber. And then this would be the magma chamber of a supervolcano. And these supervolcanoes in southern Bolivia weren't discovered until the mid to late 70s by looking at satellite imagery. They were just too big and too remote for anybody to really know that they were there. Just more reference so we can appreciate the size of these supervolcanoes. A supervolcano is 10 to 20 times larger than the eruption that produced Crater Lake 7,000 years ago. 7,600 years ago. So the calderas here that produce Crater Lake is 6 miles wide. For reference, the caldera that formed after the eruption of Yellowstone 640,000 years ago is about 53 by 28 miles wide. So these are just on an entirely different scale. For reference, Mount St. Helens or Laualatla erupted 1 cubic kilometer of magma. Yellowstone, 640,000 years ago, erupted 900 cubic kilometers. These are just completely on another scale. Still sticking with Yellowstone here, this shows the ashfall distribution from that eruption 640,000 years ago. Okay, so our study, we were trying to figure out how big each of these eruptions were, and then the exact timing of the eruption. I went down there with colleagues from Universidad Mayor de San Andres in La Paz, Bolivia. We ran into quite a bit of car trouble. We started out with 2 cars, This one just wasn't holding up. So we had to ditch a couple students. I felt bad for that, but they took a bus home. And then the rest of us fit in this little Land Rover for the rest of our trip. It was pretty exciting to, you're down here at the side of the road. You think that, maybe you're going to die up here. It's extremely remote. It's extremely dry. You can't see anybody for miles. And then all of a sudden someone comes by on a bicycle. This is one of my favorite scenes I had up there on the altiplano. I had no idea where she came from, where she was going. I didn't see any towns on the map for many miles. And she wasn't even on the road. She was just going on the side of the road. So that was pretty fun. The rest of us we fit in, I think we had six geologists in this car, plus 2 weeks worth of gasoline, water, and food to the top. And yes, that is tilted downward from all the weight. Oh yeah, so I can't remember if all three of those are gasoline. Some were water. I can't quite remember the difference between gasoline and water. But I was in the back and the roof was dented inward from the weight of the gasoline on top. And it was a little bit sketch to be right around that bump, and you can see the roof almost wanting to cave in on us. But it was worth it. The views up there are spectacular. The base elevation here, I think we're kind of around like 14,000 feet just here. Actually, it might even be a little bit higher than that. And then the peaks go up from there. It's a really strange climate. The sun is super intense because we're in the tropics. It's nearly directly above. But we're at really high elevation, so it's colder. And then the wind is just brutal. It's just extremely powerful wind. But if you can find a little place next to some rocks where there's no wind and you kind of get a little eddy there, you instantly have to just take off your wind jacket and your pants and just all of your layers because it almost feels like a nice summer day. So it's really extreme weather it's kind of hard to get used to. Doesn't really make sense. It's cold, it's hot, it's sunny. It's all of those things at once. Here's another image of us collecting rocks. This is Uturuncu volcano in the background. Every once in a while, a llama or alpaca would walk by. I don't know where they were going or where they came from. There's some of the volcanic domes. These are fairly recent eruptions. I think there's only about 12,000 years. I might be forgetting that. They're fairly recent. There's me. This gentleman in the orange is one of my colleagues I've been working for the last 15 years, almost 20 years together now. We've been working on volcanoes of Bolivia. Not a lot vegetation. There's some Yarreta, which is this really kind of hard kind of moss plant, which you can sometimes come across, but not a lot of vegetation, especially up here. You can see there's a little bit of vegetation in some of the valleys here. There's a bush. That was one of the towns we stayed in, Catena Chico, kind of a typical village of this region. And this is one of our hotels we stayed in for the night. Okay, so after we collected our samples, we took them back to Corvallis and Oregon State University and the University of Madison, Wisconsin. We got some ages, and the MA here is millions of years ago. So we kind of pinned down the volume of these eruptions and their ages. For reference here, Pastos Grandes, a fairly recent supervolcanic eruption 2.9 million years ago with a full 1,500 cubic kilometers. And just to kind of get a sense of how big these volcanoes are, Volcan Uturuncu here, that's just a normal volcano, like the size of Mount Rainier, Mount Tahoma. And then this is the caldera deposit left behind after the Vilama super eruption about 8.5 million years ago. And I made a map of those. So this is an example of some of the maps I've been making of the geology in Bolivia. Of course, you can color them. Okay. After that study got done, me and my colleagues decided to keep going, study some more volcanoes. And we looked at Tanupa volcano, which here is kind of on a peninsula of the Salar de Uyuni. And it's about 70 miles to the east of the main trend of volcanoes of the Western Cordillera. So one of our questions was, why is it so far to the east? What's it doing over there? And how is it related to this plateau? I'll just show you some more pictures here. Our university vehicle on the Salar de Uyuni and Tanupa volcano. My friends and colleagues from Oregon State University came down to help me, I should say came up to help me collect some samples. And my friend Alvaro also came out to help me collect some samples. Here's me collecting samples. I brought a lot of these rocks from Bolivia if you want to come up and have a look at them. This is where they grow quinoa. Maybe you've had quinoa, it's delicious. Despite what they say, you are not harming Bolivian farmers by eating quinoa. By all means, eat all the quinoa. It's great for Bolivia. Okay, after that study was done, I was very interested in this region. I managed to get a fellowship at the University of Durham to continue studying the volcanoes of Bolivia. And where we started our previous study of just one volcano, Tanupa, we decided we needed to do an entire transect here to study all the volcanoes between the main trend of the Western Cordillera and all those, to see if there was any differences that we could find that might give us a clue as to why the volcanoes are, or why even have volcanoes further to the east. Went out again with Nestor Jimenez. He's my one of my primary colleagues, some students and other professors at from Bolivia. More car trouble, but this time we collected 68 samples from 21 volcanoes. Here are some of the volcanoes we are sampling here on the Altiplano. I got a publication out of there. I'm not even going to try to read it, or not even try to read the title. It's open access, though. If you want to read that, I encourage you to do so. Just more examples of sample collection on the Altiplano. We found this volcano was about 3.8 million years old. These lavas that I'm hitting a hammer trying to get a fresh sample were about 2.3 million years. We brought these rocks back. So these are these rocks I have up here. And this is a slice, a thin section through the rock. So it's just a thin slice cutting through the rocks, showing us the crystals in there. Did a lot of chemistry of these lavas. I'm not going to talk about these, just wanted to show you what we do. We look at a lot of chemical analyses of volcanoes, and this has the ages and then their distribution. We got 23 new radiometric ages. Volcanoes in this region range from about 1.2 to 26 million years old. And we came up with a kind of a model to try to explain why we had these volcanoes where we did. Might get a little bit, I'll get into that a little bit more in just a moment. So some of the bigger questions that geologists are interested in with this plateau, the Central Andean Plateau is the second largest crustal plateau on Earth. It's second only to Tibet and the Himalayas in size and elevation. And we don't even really know why it's there. So to try to figure out why we have this big plateau, which influences so much about our weather and just the kind of the distribution of life in South America. That's why a lot of geologists are trying to understand this region, because it really shouldn't be there. Its tectonic situation does not suggest there should be a giant plateau. Yes, Paige. There's definitely a lot of planning in advance. The question was, when I go to Bolivia to collect samples, is there planning? Yes, there's a lot of planning. It takes quite a bit of effort to get there. So beforehand, I talk with my colleagues, and I'm on Google Earth a lot, looking for places that are at least somewhat close to a road, because it's a lot of effort to walk and then to go up you have to hike up the mountains. It's just extremely taxing at that elevation. So yeah, we try to plan out the most we can, but sometimes you can't plan out when you're there. You just kind of have to see where it takes you as well. Yes, sir. Ah, let me give you some rocks. So the question was about samples. Let me go back to that slide here. So the samples you see on the surface tend to be a little bit weathered from the atmosphere, the moisture, and so they're not very fresh. So we need to get a hammer and break into the center of the rock to get a fresh piece of that rock that hasn't been weathered by the elements. There we are. So using a little microscope there to try to look at the crystals to see if it's in a suitable rock. You don't want a rock you need a good fresh rock. So we spent a lot of time with the hammers. You can see I've got a big sledgehammer here, and that will crack the rock open. I think this rock here is actually what we opened here. Sometimes you have to get some pretty big rocks open. And then from there, you use the medium size sledgehammer. And then, see, is there a picture? I'm not sure. Then you have to use a smaller hammer to get your final sample. Yes. Oh, I taped them up so I could put a sample number on them. The tape you might see a sample number on there. Yes. Also, it's a little bit to protect them from bumping into each other. So I came home with a couple 100 pounds of rocks, and I had to put them, I had to ship them. In this case, I was shipping these to the United Kingdom. So it was kind of a lot of effort to ship rocks from one continent to another. They're very heavy. Okay, so why is there even a crustal plateau here? Why does the Altiplano even exist? It doesn't make a lot of sense. If you're in one of my geology classes, you'll recognize this deep sea trench as from a subduction zone. The Nazca Plate is moving eastward here where it meets the continent. And in normal cases, the oceanic crust just sinks down into the mantle and does not create a crustal plateau. Typically, when we get crustal plateau, you need to have two continents colliding, which we have here, where kind of the Indian crust is moving up into the Tibetan crust. So we have completely different plate tectonic settings from Tibet. Tibet is a continental collision zone. Central Andean Plateau is at a typical oceanic crust subduction boundary. And you might be familiar with this type of boundary. Because this is what we have going on here in the Pacific Northwest. We have a subduction boundary you may be familiar with. So it's a very similar tectonic setting as we have in Bolivia. But you may have noticed we don't have a 14,000 foot elevation plateau here. So the question is why? Just for reference here, there's the Indian plate slamming into the Eurasian plate. Two continents colliding is what you usually need to create a big crustal plateau. Here we have oceanic crust moving into the South American plate, not your typical situation. What we do know is that the western part here of Chile is being pushed into the rest of the South American plate, creating a lot of compression, and that's what's creating our plateau here. So we know how it's happening, and I'll get into it. We kind of know when it's happening, but the overall reason of why it's happening, there's a few hypotheses out there, but none of them have full acceptance. I just want to go into that just a little bit more here. This is the Eastern Cordillera. So over a span of 300 miles, we go from about 1,000 feet to 12,000 feet. And so Nadine McQuarrie, a professor of geology, University of Pittsburgh, put this cross-section together. So this is what the Bolivian crust looked like before it was shortened. And then after it was shortened, it's pushed together, and it's now about 200 miles shorter than it was before. So zooming in just a little bit to see what this looks like. Here's before the shortening, then this is after. And that black line here is the modern surface. So I'm going to zoom in a little bit more here. You can see there's a lot of faults, a lot of folds, and then this is the modern surface. I'll get rid of that. So all that material that I just kind of removed there, was removed by erosion. It's now probably in the Atlantic Ocean, the Amazon River. So here's kind of the before. So we lost all that rock. You can see these huge folds. And so folded rocks give us these anticlines and syncline. A syncline is kind of a smile. Anticline is kind of the opposite of that. You see just a lot of these folded rocks here in the Eastern Cordillera. It's one of the best examples on Earth where you can just really see the crust just crumpling. Like if you have a carpet and you kind of push it together and just get a crumple, it's kind of what's going on here. You can zoom in and just see all these folds. And this gives us this tilted sedimentary rocks. This is me on the side of a tilted sedimentary rock. You can see there's ripple marks. So this is mudstone. This was deposited in a lake or a shallow ocean. And of course, it was flat when it was originally deposited. Now it's been tilted on its side. Can't really see it, but maybe you can see the anticline here in southern Bolivia. I want to show you some of these synclines. I'm going to go through each of these. The Inca Pampas syncline is this just amazing structure in the Eastern Cordillera. Here's kind of a side view. You can see in the center here, we've got non-tilted beds, and we've got this syncline where the sedimentary layers are tilted into a U shape. This is what it looks like from the ground. And I'm going to put on the kind of just the stratigraphy there to show you where these layers are, the angle of the layers. So over a fairly short distance, is about 10 miles across, we've got this big U-shaped structure. And here's what it looks like on a geologic map, where the youngest rocks are in the middle, and then the older rocks as you go away from that U shape. So in this case, we've got almost 400 million years, not continuous, but 400 million years of rocks preserved in this area. This syncline here, the Moraga syncline, close to the judicial capital of Bolivia, Sucre. Here's a side view of that. Another one of these synclines with flat beds in the middle. So looking to the west, we've got these tilted beds. But in the center, you can see the sediments are almost perfectly flat. And then to the east, they're quite tilted again. And quite famously, in some of these beds, these are full of dinosaur tracks. This is Calorco, Bolivia, which might have more dinosaur footprints than any place in the world. Thousands of footprints have been found here. This is, I had a chance to visit a while ago. It's about 68 million years old. You can see those are some pretty big sauropod footprints. So these footprints were put down just a few million years before the dinosaur extinction. This is what it would have looked like 68 million years ago. Of course, it was flat now, or sorry, it was flat when they were deposited. They've since been tilted by the mountain making. Cool national park there. They've got life-size structures of the dinosaurs that must have made the footprints. And here's one of the largest ever theropod footprints ever discovered. And a scene of what that might have looked like. Okay, another great place to visit, the Toro Toro syncline. You can see another big U-shaped valley, inclined beds, and full of dinosaur footprints. So especially those in my Geology 101 class, if these sediments have dinosaur footprints in them, and then those sediments were tilted, how old must that tilting be? Older or younger than the dinosaurs who walked there? Let's see here. So what happened first? Dinosaurs walking in the mud, or the layers were tilted up into big folds? Right. So we know that the tilting must have happened post dinosaurs, which gives us a starting point of when this tilting happened. And so here's these dinosaur tracks throughout the Eastern Cordillera. Most of these are now tilted. So we know that the plateau itself is younger than dinosaurs. So it's younger than 66 million years old. Here's what South America must have looked like about 66 million years ago. The whole continent was basically fairly close to sea level. Yes, sir. Yes, exactly. Pangea would have already been separated by this time, but so it would have been an island at that time. So for the Central Andean Plateau, we know that it began to form less than dinosaur time. Looking at the fossils, we pin it down to about 60 million years. In total, across this whole thing, about 330 miles has been compressed. That gives us an average rate of about 1 centimeter per year. So 330 miles seems like a lot, but 1 centimeter a year also seems doable. And then kind of putting it all together, we're trying to figure out like why this plateau formed, when it formed, and then how volcanoes are related to it. That's where I come in and try to kind of look at the volcano contribution of this. And kind of our going hypothesis here is that we might need these types of large crustal plateaus to actually form continental crust. Because if you get a giant plateau forming, the lower crust, which is high density basaltic composition, actually becomes more dense than the mantle beneath it and will actually sink down into the mantle, and we'll lose our basaltic lower crust, and this will make our continental crust more felsic and more buoyant. So there's an idea out there that we actually need these giant crustal plateau in order to form the continents. But there's still a lot of work, and we're still trying to put it all together. And with that, I will conclude my talk and ask for questions.
All right, I'm coming around with the microphone to get the questions.
What's felsic?
Yeah, I kind of jumped into felsic is a low density rock. That's what the continents are made out of. So most of the rocks on land is a felsic composition, meaning it's low density. So essentially, when magmas rise up, they're high density mafic rocks, which is the opposite of that. That's what the ocean crust is made of. And those kind of get stuck here in the lower crust. And unless you have a plateau growing, you can't get rid of that lower crust. So this is kind of a way of getting rid of that dense lower crust that would normally be there. And over many millions of years, hundreds of millions of years, with multiple plateaux around the world, we can kind of reduce the density of the overall continental crust. Yes.
So I have a question about cloud forests because we've been talking a lot about forests in our earth science class, but I don't think that has been addressed before, and I'm kind of curious about what that entails.
Cloud forest is generally a term we give to kind of a high elevation forest. So it's kind of in the clouds all the time. So generally we think of like tropical rainforests being low elevation, closer to sea level. But then up in the mountains, if you get a lot of rain, you're kind of at cloud elevation. So you're in the clouds a lot. So it's basically usually a tropical forest that is at higher elevation. So lots of orographic rain. Could I breathe? No, that's a great question. No, that's a very good question. The short answer is yes, I could breathe. The longer answer is not very well. There is I don't remember the numbers, but you're losing a lot of oxygen at that elevation. I remember I went out with my friend Alvaro, and we're in the car driving, we see the mountains, and there's no one out there. And he's just like, why are you the only geologist I know out here studying? I was like, I don't know. This place is just beautiful. There should be hundreds of us. And then like 4 or 5 hours later, when we were up on the volcano, just sweating, dying, can't breathe, no water. I'm like, okay, this is why there's so few of us up here right now. It's a challenge for sure. There's way less oxygen up there than down here at sea level.
Okay, if we get just I don't want to get too technical, but how do you do dating? How can you tell how old something is?
So radiometric dating takes advantage of radioactive decay, but so over time, well, a crystal will have a radioactive element in it. The best example is uranium. So a crystal, when it forms, can have uranium in it, and over time, that uranium will decay to lead. It'll decay to lead, and that crystal, when it's formed, doesn't have any lead. So all you do is measure the amount of uranium, the amount of lead, and if you can know where you started from and you know the decay rate from uranium to lead, then it gives you an age of that crystal.
All right, well, thank you so much. Thanks to our audience. And we're out of time, but if you have any further questions or you want to look at the samples,
Yep.
please come up forward.
I'll be here for another 10 minutes or so, and then we'll go resume our class.
All right, and thank you all, and join us again next week.
Thank you, everybody. I'll be sure to answer questions and show you some rocks if you're interested. Yes,
The town you showed.
yes.
People there do for a